So we are going to get into intensity and color. Today we're just going to start on the intensity piece of it, and then we'll follow up with the color piece of it, which is probably the more fun piece of it on Monday. But intensity and color of light. So we have all seen that image right there, and we're going to talk about that towards the end of this section. So how many colors are there? It is a spectrum of colors. So the rainbow represents our Roy G. Biv. If you had art in elementary school and you had to learn all the colors of the rainbow, right? But what you'll notice about those colors is they blend from one to the next, right? And so if you ask how many colors there are you talking about specific primary colors, secondary colors? Are you talking about a blend of all of the above? And so the first thing we're going to talk about when we talk about light is, remember, colors come from light. And so we talk about light. There are many ways to describe the energy of light. So last section, we talked about the fact that light is energy. And so we are going to talk about how then do we describe it. We want to be very specific in how we describe it. And so there's all these terms thrown up there. And so we're going to say, if I have light, then what am I going to tell you about the light? The first term we're going to talk about is called luminous flux. It's the visible light energy that leaves a light source per second in all directions. The total visible light energy is measured in something called lumens. And it is going to be a standard unit that we're going to use. But light emits their light in all directions. So sometimes we are looking at a specific direction that it goes in. But when we refer to the flux, we are talking about in all directions that it leaves. So we have two ways that we measure this. And I don't know that you had to fill this in. I think this is just in your notes. Luminous flux is measured in lumens. That's how we're going to measure it. That is the standard unit. And that is a measure of power. So luminous flux is a measure of power. The next thing we're going to talk about then is the intensity. The intensity is the rate of light energy emitted by a light source in a specific direction. So flux is in all directions. Intensity is in a specific direction. We often think of this as the brightness of it. So we often think of intensity as brightness. Intensity as brightness. Luminous intensity is thought of as the brightness. And the way this is measured is called a candela. Candela. It is abbreviated CD. CD. Give you this. You do have a spot to write that equation. We're going to do the math part of it on Monday, but you do have a spot to write your flux, which is that Greek letter there, the flux, and then multiplied by your V divided by 4 pi. All right, the next term we're going to talk about is luminance. It is abbreviated LV, and this is actually supposed to be a subscript, by the way. It did not subscript on mine. It's supposed to be a subscript there. Luminance is the rate of flow of light energy emitted by a surface in a given direction from the source. Rate of flow. So now we're talking about how quickly it is moving versus just the light source in all directions, the rate of energy by a specific, and now we're talking about rate of flow. Rate of flow is your luminance. So luminance is measured in units of power per unit of area. So units of power, that's your candela. Unit of area is meters, and that also is a superscript squared. Candela per meter squared. Candela per meter squared. So we're actually talking about movement here, almost how you would think about velocity or acceleration, right? We're now talking about it as how the power is measured for the luminance. Illuminance. And we're going to use all of these in formulas. And the illuminance then is the lighting value at a particular point in space. You may think of it like illuminate All right, if I am trying to put light on a specific point, I will illuminate it. Illuminance, all right, is the lighting of. All right, so you can think of it like a spotlight on a stage. The illuminance is the lighting value of a specific point. If I have an actor on a stage, I am going to illuminate that actor. That's where we are getting that term from. So all terms you've probably heard before. So let's talk about the brightness of a light. With a luminous, the focus is on how well a light illuminates a surface in equation form. In equation form, we have phi, which is that term or that Greek one that we did for flux. All right, times V over A, or the area, which is, we're going to do R squared though. And again, we're going to do all of this with the math piece of it. It will not be on your quiz. What I want you to look at is the unit of illuminance. So they've given it multiple ways. The candela is per meter squared, the luminance per meter squared, but it is also called a lux. That is a new unit term. That is the unit for illuminance, is lux, LX. All right, so let's look at the summary of all of these crazy terms that you can go back to if you need to. These are the 4 terms that you're going to need to know from this section. Luminous flux is the total visible light emitted. Luminous intensity, that is the visible light emitted in a particular direction. Luminance is visible light power emitted per unit area. And illuminance is the visible light landing on a specific surface. So they sound very, very similar. So you need to distinguish in your brain what the difference is. The difference between the flux and the intensity is all directions for flux, specific direction for intensity. Luminance is the power that is emitted, but then illuminance is I'm emitting it onto a specific object. You'll see to the right are symbols there. All right, we do have phi, which is our little Greek symbol here. And the V are all your visible light there, but you have that. You have your L for luminance, your capital L for intensity, your capital L for luminance, and your E for illuminance. And then notice your units. Lumen is your units for your flux. Candela is for the intensity. Candela per square meter, or it looks like this. And then you have your lux. All right. Questions on just the terms. That's why I chose it. All right, what is the illuminance? 5 meters from a point source emitting 975 lumens. All right, so we're going to use that equation that we had. We're going to use is going to be that lumens, which that is not how you draw that. It's like that with a line through it. I'm just going to do it this way. Circle, line. All right. And then it's going to be 4 pi and your radius squared, or how far away you are from the source squared. That is the formula you're going to use for this over and over, depending on what you're solving for. All right. Which in this case, we're solving for the EV, the illuminance here. What is the illuminance? That's what we're solving for. 5 meters, that's going to be our R, or our distance. 975 lumens, that's our little guy represented by lumens there. So here we just plug it in. I mean, it's pretty straightforward. You're going to take 975 lumens. You're going to divide it by 4 times pi times your radius, which is 5 meters squared. All right. You're going to get lumens per meter squared, which is lux, LX, when you do this. And again, this is 2 significant digits. So when you put it in, you should get about 3.1. This is lumens per meter squared. That unit, lumens per meter squared, is lux, LX. That's just a unit measuring illuminance. So you would say 3.1 lux. LX is your abbreviation for lux there. What's the luminous intensity of a light source if it produces an illuminance of 85 lux at a distance of 1.5? So this is the same question, but this is why your terminology is super important, all right? Luminous intensity, that is your little Greek letter, right? LMs, right? Over your 4 pi r squared equals your EV. Well, your EV is your illuminance, okay? So it's really important to know what they've handed you and what you're solving for. They have handed you then your little illuminance. They have handed you your R. What is they are solving for? That. So we're back solving into it. You're going to set it up the same. It's just what am I solving for versus what I have. So we have our lux. We do not have that. We have our R. And so we're going to solve. All right, so go ahead and solve for that. For 2 significant digits, because you end up with like 2403, 2 significant looks like this. So in your calculator, you should have the 8.5 times the 4 pi times the 1.5, and you should be able to just hit that guy and it'll do it order of operations. Solving for our phi here. We're solving for phi, which is our luminous intensity. You're just solving for a different variable, which is exactly what's happening on the next one. If you look at example 24, finding distance, they're just saying R, the R, or how far away you are from the. So you should have set it up, your 12.5 equals your phi, which we're solving for, over your 4 pi, 3.5 squared. You would have gotten 1924. How many significant digits based on that one right there? You should have said 1900, and you don't need to underline here. That is 2 significant digits. Last example in this section. Your normal desk lamp has a standard 100 candela bulb and sits 78 centimeters away from your desk. The bulb burns out and you have only a 61 candela bulb to replace it. How far from your desk will you need to replace your lamp with the new bulb to have the same illuminance? So normally I would say pay attention to the fact that it's centimeters, but if you go back and answer in centimeters, you're going to be okay, right? So just pay attention to your centimeters, meters, because technically your lux is going to be meters, but you're just going to set 2 fractions equal to each other. We're not even going to lux at this point. We're actually just going to set them equal. So as long as you give me centimeters to centimeters, you're good. But in this case, I have one piece of one and one piece of another. So the same illuminance. So whatever that illuminance is for the first bulb that I had, I would say that my candelas, right, over my 4 pi times my radius, in this case 78 squared, is going to be that illuminance. But then I get a bulb that is not as many candelas. So now I want the same illuminance. That's going to stay the same. But I only have 61 candelas. And I need to know, what does this R need to be? Okay? So basic algebra is, if it's the same, I can set them equal to each other. So I can say, well, this guy, this 100 over 4 pi 78 squared should equal the 61 over 4 pi, and however close or far away I have to set that particular lamp so that the brightness is the same. That's what I'm trying to say. The illuminance, how it illuminates, what it's shining on is the same. So a couple things about solving for that R. The R is in the denominator, but we have equivalent ratios, so we can just flip both sides. The other thing that I want to point out is anytime you have the same thing on both sides in the same position for ratios, they are going to cancel out. I'm going to show you why, but if you just remember that, those 4 pi's are going to cancel out. They're going to. So if I flip both sides, I end up with 4 pi 78 squared on this side over the 100 equals 4 pi r squared over the 61 on this side. We good about that? So if I were to get rid of the 4 pi, I would divide by it, right? when I divide this side by 4 pi, it also goes away. Does everybody see that? So when you have equivalent ratios and you have the same thing in the same position, when you get rid of it on one side, it gets rid of it on the other side. So what happens here is this 4 pi is going to completely cancel out from this equation. If I were to divide both sides, I'm going to just go ahead and cancel him out. Does everybody see that? Then I only have to worry about moving that 61. So I'm going to multiply both sides by 61. I end up with 61 times the 78 squared over 100 equals the r squared. Notice it is r squared, so at the very end of this, or somewhere in your calculator, you're going to have to do what? Square root it. And so it's going to end up looking like that. That's how far away that lamp needs to be to illuminate the same. All right. So go ahead and do that. Calculate to how many significant digits on this? 3. Come to is the term transmittance. Transmittance is the ratio of the transmitted luminous flux to the incident flux. So materials transmit visible light differently. We know this intuitively, but we don't always define them the same way. So the first thing that we probably are familiar with is the term transparent. If you say something is transparent, you pretty much mean I can see through it. That's what transparent means. And so the material is transparent if it transmits light so that we can see clearly through it. It is transparent. But then you have a secondary term here that you may not be as familiar with, which is translucent. Translucent. This is when it distorts it, all right? It doesn't even have to distort it very much, right? But it's going to distort it. And so you've seen like a foggy piece of glass that you can kind of see through, but then it's kind of shaded. Or even if you have sunglasses, those aren't actually transparent. It actually changes the light. That's the whole point of them, right? And so transparent versus translucent is really about how much visibility you have through the process. If it's clear and it's allowing all the light through, it's going to be transparent. If it's allowing some of the light through, enough that you can at least see through it, it's going to be translucent. And then we have this other term, opaque. Opaque materials do not transmit light. Now, you may actually see light coming through opaque objects, but it's not enough for you to see visibly through it, right? And so if you look at, for example, my back door here, obviously light is coming through, but visible light, meaning can I see through it, see an object through it? I cannot. And so that's going to be considered opaque. So the thickness or the smoothness may determine which category it's in. You could have glass that seemingly is perfectly clear, but the shape of it changes the light and it does not see clearly through. All right, versus a flat maybe piece of glass that is also clear, that does not distort the light. All right, so thickness and how smooth it is may change the category. So it's just some visible pictures of what this looks like. Transparent, you can see all the light passing through transparent objects. Translucent, some of it. Opaque, none of it. And by this I mean visible. So if I looked at this little guy right here, you can see this would be if I just had like a window pane. This would be kind of a frosted window pane that I can still see through. And this would be an opaque. I can't see him at all. This may look brighter, but visibly I can't see through it. So this may look brighter than the part around it, but I still can't see the animal through. Approximately 4% of the world's population suffers from some form of color vision deficiency. It's found more often in men than women, right? Color blindness of sorts. There's a whole spectrum of color blindness. So you have people that just confuse certain colors, and then you have people that are legit colorblind, where it's like grayscale almost, right? And it depends on, I mean, this is more of a biology thing. It depends on the cones in your eyes. I think they talk about it a little bit. It has to do with just the primary. We're going to talk about the primary, quote unquote, blending colors, and then the secondary. And it just, the way light works is kind of opposite of what we think sometimes. So there's different ways that we receive light directly from a source. All right, someone shines a light in your eyes, the sun directly from a source. Reflection from a surface. All right, so you look in a mirror, you are receiving light through a reflection in a surface. And then transmission through a material. All right, if you've ever worked with staging lights use filters to change colors. And so staging lights often are through a material. So our eyes have cones that measure the intensity of blue, green, and red light. Blue, green, and red light is how our cones receive that. And so these red, blue, and green are called additive primary colors. Additive primary colors. Magenta, cyan, and yellow are additive secondary colors. Secondary colors. And you'll see in here, so you see the primary out here, and you see how they blend, right? You see and these are additives, so you see the 3 secondary colors appear there. Combinations of these can produce any color except black. All right, except black. What's fun fact, and we talk about it, but the combination of all the colors is white. The lack of all the colors is black, right? Which we think opposite if we've ever used a crayon, right? But that's actually how it is when you're talking light passing through it. And so a mixture of all 3 of those primary will produce a white light. So we then have complementary colors. Mixing certain additives secondary to a primary will make white light, and they're called complementary. So you'll see that when the red and the green overlap, that those, all 3 of those in the center. So when you have certain ones, if you mix an additive with a secondary and a primary, then they create white light together, and it's because they are a combination of 2 of the other colors. And so, like if you do the blue and the green over here, you're going to see the cyan. So then if you do cyan and red, that's all 3 of them, right? So cyan is made up of the blue and the green. So then if you cross the cyan color with red, you're going to get white light because you just got all 3 of them. So then here you have red and green give you that yellow. So then if you mix the yellow with the blue, I know yellow and blue make green when you're coloring, but we're talking about additive light through it. You're going to get the white light there because you have 1, 2, 3, all of them. And then if you see that the red and the blue give you that magenta, so then if you mix that one with the green, you're going to get the white there as light goes through it. All right? And it all has to do with your absorbing or reflecting of these colors. So the first term here is pigment. I think it's actually the next blank as well, but it's a substance that absorbs certain colors and reflects others. So when you see, and we'll show you the picture, but when you see a red apple, it's actually absorbing all the other colors. It's reflecting the red. And that's why you are picking up on that color from that object. It's absorbing the other 2. It's reflecting the one that you see. So a pigment is named for the color it reflects. So we have that formal definition of pigment, but pigment is what you're seeing reflected, the color that you're picking up on. So what happens if we illuminate an object with a certain pigment with the same color of light or a different color of light? All right, so what they're asking is, well, if I take one object and I light it up different ways, what happens? And so I have a red apple, all right? if I put a red light on it, you still see the red. But what happens is the leaves all of a sudden have something different going on, because now I have put in red into something green. And so then this sky is going to darken, and then you'll see it flip. The red darkens and the green. And then if I put a blue, we see that we've blocked both of those reflections. It should be reflecting red here. It should be reflecting green here. And it's kind of messed up both of those. And so as we light up things through these filters, which is what I would like to do on Thursday, is do this with actual filters. But when we light up based on different filters, you're going to get a different reflection back on you based on what the original absorption was in just a white light and just a normal light that comes through. So then let's look at subtractive color mixing. Subtractive color mixing. Cyan, magenta, and yellow then are the subtractive primary colors. Red, green, and blue are the subtractive secondary colors. And combinations of subtractive can produce anything except white. And so now we're talking about taking it back out and how many colors are there? So then when you think about how many colors are there, it's a combination of, many, many colors. If you've ever done anything with coloring and computer-wise, you know that there are different levels of how much color is available based on your unit, based on your monitor, based on all of that stuff, right? When you print, if you've ever had a printer, typically the printer actually has cyan, magenta, and yellow cartridges. Why? Because those are combinations of the other ones, and then by combining, so you have all of them when you have those three, because those three come from two of the other ones, right? And so then all of a sudden they can print all the color you want from those three, right? Because that's a combination of all the three primary additive ones. And so by doing that, you can make all the colors that you're trying to print using those three. All right, so millions, intensity, the blending of it, and our ability to be able to receive it are all parts of color.